So last time we were reviewing the concept of force, and we ended up with this homework. So now we're going to see some special forces, the common forces, the ones that we find easily in everyday activities. And we are going to start in weight, what in Spanish is peso. That's why here there is a P of peso, and in these examples too, but later on we're going to call it, and I'm going to change it already, W from the English word weight. What is it? Well, this is the gravitational force due to some particular planet. In our case, we are on Earth, so the weight is the force with which the Earth attracts the object. So it's the gravitational force of one object on Earth or on any other planet. But we have this formula to calculate it, and we say that here this is the force, this is the gravitational force, weight, okay? And this is the mass of the object, and this is a small g. What is this small case g? G is the acceleration due to gravity. And if we are on Earth, that's 9.8 meters divided by the square second. Okay, this should be, I'm going to change it already because this should be uppercase, like this. Okay, so it's an acceleration. In here, we have all the information about the radius of the Earth and the mass of the Earth, and everything is inside this acceleration. So it means that all the objects feel the same acceleration, which is 9.8 meters divided by square seconds. And if we multiply this acceleration times the mass of one object, we have the gravitational force that that object feels on Earth if we are using this data here. So let's see some examples. If we are calculating the weight of an object of 200 kilograms, remember the unit for mass is kilograms, not grams, we just multiplied 200 times 9.8, and that gives us 1960 newtons, because remember Newton is the units for force. Then the same, if we want to calculate for 500 or for 700, we will have to multiply the mass times the g, that's 9.8 on Earth, and we will have the force. In the case of 500, it's 4,900 newtons. In the case of a mass of 700 kilograms, we have 6,860 newtons, and yeah, so that's about it. That's the weight. But the weight changes in other planets. Maybe you have heard the weight of an astronaut is not the same in the moon than on Earth, and it's true because the gravity, so this g, is different. So the acceleration due to gravity is different. Sorry. And you can see it changes. The smaller the planet, or the less g. And of course, Jupiter, this is something huge. And the same astronaut will have the same mass, 100 kilograms, in every planet, but the weight, which is a force, is not the mass. The mass is kilograms, but weight is not kilograms, it's newtons, because it's a force. That's why the weight is different in every planet, because we have a different g for every planet. And if you do it, you feel less attraction. That's why they look like jumping when they are on the moon, because they feel less gravitational force. They feel only 160 compared to 980 on Earth. So that's why we say astronauts have less weight outside the Earth in the moon. No one has ever gone to any other place, like no person. We have sent robots to Mars, to Venus, and to some planets, but they have not landed, just are orbiting around. We have just landed in the moon, in Mars, and in Venus. So, and people only on the moon. That's our level. So, really not so impressing. Well, anyway, that's great. The gravitational force. Another very common force is the driving force, and I put this in Spanish because you don't have it on the book. It's just for you to know. This is the force that is made is exerted by the motors. That's why in Spanish you call it fuerza motriz, and you put an M here because it's the one that makes the object move. It's the motor, the engine force, the driving force. Another important one is the friction force, and friction is due to these irregularities in the floor. So when we think something is flat, really it isn't, and you have some irregularities, okay? And that's why when you push something, you feel some resistance, and that's the friction force, okay? In Spanish it's fuerza de rozamiento. And yeah, so it has an electromagnetic origin, but we are not going to see it why. Just know that if you zoom in, you're going to see these irregularities, and of course you can imagine it's like when you have the shoes that are totally flat or with spikes, and it's more difficult to slide if you have spikes. So because they have more friction with the floor. So anyway, the friction force. It always acts against movement because it resists to the movement. So that's why we draw it in the opposite direction. So if we move it to the right, we're going to draw the friction force to the left because it's opposing the movement of whatever we are moving. And well, that's here you can see also that the skaters, they are coming forward, so the friction force has to be drawn backwards because it's opposing to its you have to draw it opposite to the movement, so backwards in this case. And that's why you need to keep on pushing, because if you don't keep on pushing on ice, you slow down until you stop completely, and you stop completely because you always have this force trying to stop you, always, because of these irregularities again. And you can see it also in billiard balls. When you're playing pool, they're going to stop at some point, and they stop because again this green mat has some irregularities, as anything else. I mean, there's nothing like a perfect flat surface. It doesn't exist. Another common force is the normal force, and this is a very complicated one at first, but I need to tell you about it. So a normal force is the one that keeps things from not falling, and I'm going to say what I mean by that. So if we place an object, such as a book, on a surface, for example, on a table, the surface exerts a force opposite to the weight, holding up the object. Of course, because we know the weight, el peso, exists, and if we only have this force, the book is going to go all the way down, breaking the table and continuing till the ground. But it doesn't happen. So why? Because we have a force contrasting this effect, okay? And that force is the reaction of the table against the force that we are doing with the weight. So it's a force that is always opposite to another one that you do against the surface, and it's called the normal force. And normal is not because it's common, the like normal one, but it's because normally in mathematics it means perpendicular, so it means a perpendicular force. That's the meaning of normal in mathematics. Sorry. Here we have another example of this flower, and it's on the table, and again it doesn't break the table because the table is making another force to contrarrest the weight, and yeah, that's the normal force again. So you just need to know how to draw these forces, okay? Just that. Tension. That is the one that happens when we have cables or ropes, so something that you can use to pull stuff up or left or whatever. So is the force that you have in the cable or in the rope. That's tension. And yes, we say that la tensión de la cuerda, so in normal speech we have that concept, but it's a real force and it's always going in the direction of the pulling, okay? Yeah, here we have drawn the weight because it's always there. Weight is always there because we are always on Earth, so we always feel gravity, and we should draw it in every drawing that we have, but yeah, so it's only here, but it should be here and here and here because it's always there. Another common force is the elastic force, and this is the force exerted by an elastic object in order to return to its original shape when it has been deformed. So imagine we have this spring, and this is the normal shape for the spring, the natural shape, okay? Now if we stretch it, it's going to be longer now, but the string is going to try to return to the original shape. The force that tries to take the object or take the spring to the original shape, that's the force that we call elastic force. If we do the opposite and we compress the spring, again the spring is going to try to return to the original shape, to this shape. So it's going to exert a force so that it becomes again this spring where it has his natural shape. So again, this force here is the one that we call elastic force, and it's done by the object to return to its original shape. And here we have also drawn, this is the weight, okay? This one here in red is always with the weight because it has, always we have the earth acting on every object, so we're going to have a weight, and we're going to have a normal force also because this is on some surface, so we're going to have the normal force. Every time we have a surface, we have a normal force, and so that's why these two are here. And when we stretch or compress the spring, we also have the elastic force acting. One more force. This one you have maybe experienced in your fridge. Maybe you have experienced this force in your fridge because I'm sure you have magnets. And okay, so this is the electromagnetic force. So it's the one that makes magnet work, and electro for charges, okay, for electricity and so on, charges. So it can cause attraction or repulsion. You know it because you have played with magnets and you have played to have them attracting each other or repelling each other. So you know how it works for magnets, but you can also use it with charges. And you know, two charges of the same sign, they repel, even if they are two positives or two negatives. but if they have a different sign, then they attract. And this is for gravity, like for masses. Masses are always attractive, but yeah, I was meaning to explain only charges. Also, if we can charge stuff that is not charged in the beginning, like balloons, and we can attract objects like the hair, or small papers. You can do it also with the pen. You can do this, and I would do it if we were in class, but yeah, so far I don't know when we will be back. Anyways, the electromagnetic force. And I wanted to say, because we saw it here, but I didn't mention it, that an object is in equilibrium when the forces acting on it compensate each other. So here you all understand this game. It's a game where you pull and you try to win by moving the other team a distance here. But you have, for sure, I'm sure you all have played this game, and if you pull the same amount on one team and the other, you don't move at all. And you don't move not because you're not doing anything, because you are pulling, you are applying a force. You're not moving because you're applying the same exact force as the other team. So when you do the same force in two directions, in two opposite directions, you're not going to move. You're in equilibrium. Okay, that's what happens here. So the jar here doesn't break the table because this weight is compensating with the normal force. So we say this object is in equilibrium. And that's all for now. These are the homework for Tuesday after class, Wednesday 15th, I think. I will check it out and put it on the webpage, but this is the new homework. And have a nice Easter. This is to do it, I mean, it's only 3 exercises, so you can do it on when we are back. So on Tuesday already, you can start working on it. But I wanted to, because I have been working on this presentation, and I wanted to post it as well as some tests from Wikipage that I'm just going to upload in a few minutes. Have a nice Easter, and I hope you can enjoy it as much as you can, given this situation of the quarantine. But yeah, let's see what we can do about it. See you!